Okay, so welcome back, everybody. Um, Here's just to remind you, yesterday I ended with a statement of the multinomial theorem. It was clear, where we were headed with this, with these multinomial coefficients. They arose in our first examples, clearly a generalization of the binomial coefficients. And we saw how in the case of having two of these k's, this was actually just a binomial coefficient. So I was debating over whether or not to do the proof. I am going to do the proof just to show the similarity in structure between this and the induction proof that we use for the binomial theorem. So next time is now. So let's do this by induction on n. Clearly holds for n equals 0. Check if you do not believe me, but this is not a very interesting expression when n is equal to 0. But nevertheless, these left-hand side and right-hand side are equal when n is equal to 0. So that's our base case. Suppose that it is true for n, some generic n, and we want to show that it is true for m plus 1. Right? This is our most basic form of induction here. So let's compute the following. How do I want to do this? Let's see. Maybe just to keep this a little bit more tame so you can truly see what's going on, maybe what I'll do is, instead of doing it for the completely generic case, let's just do it for the m equals 3 case. This will make it clear what it is that's going on. You could do it for the generic m case in a number of ways after this. You could even do like a double induction if you really wanted to do that. But no need. Let's do it when there are three terms here. So when there are three terms here, this expression, again, this is going to hold whether there are three or m terms here when n is equal to 0, so the base case consideration is the same. But what is true when m is equal to 3, this expression just involves 3. I'm just going to label them x, y, and z. So if x plus y plus z to the n plus 1, what is that? Well, this is x plus y plus z times x plus y plus z to the n. But I assume that this multinomial theorem in this case is true for n, so this could be rewritten as x plus y plus z times the sum over integers a, b, and c, such that a plus b plus c is equal to n of the trinomial coefficient n, choose a, b, c here, times x to the a, y to the b, z to the c. Now, the idea here is the same idea that we had in the binomial theorem case, which was we distribute this sum to each of these terms. So rewriting this, I'm going to go ahead and do the addition here. So I'm going to do or sorry, I'm going to go ahead and do the simplification here where I have moved x inside, moved y inside in the second term, and z inside in the third term. So I get three sums. Right, so I get a sum over integers a, b, c, such that a plus b plus c is equal to n of n choose a, b, c here times x to the a plus 1, y to the b, z to the c, plus sum over the same integers n choose a, b, c. Here, y is going to be the one that gets incremented. So this is x to the a, y to the b plus 1, and z to the c, plus one more term. Again, sum over integers a, b, c, such that a plus b plus c is equal to n. N choose a, b, c. X to the a, y to the b. Now it's z to the c plus 1. Okay. And so the idea here is the same that we had for the binomial case. It is that through reindexing here, I can rewrite these as follows. By grouping like terms, I can rewrite this as a sum over ABC such that a plus b plus c is equal to n plus 1 of the sum of three trinomial coefficients n, choose a minus 1 b c plus n, choose a b minus 1 c plus n, choose a b c minus 1, and all of those are multiplied. Here, let me draw a line here because these are going to run together. All of these are multiplied by x to the a, y to the b, z to the c. Where does this come from? This comes from reindexing each of these sums to ever so slightly. Okay. Okay. So what do I mean by reindexing? It's that in these sums, an instance of a plus 1 is replaced with a, but this is really replacing a with a minus 1. Replacing a with a minus 1, we have a minus 1 here. 1 gets added to the other side. Right? Replacing a with a minus 1 here, this would be a minus 1 plus 1, so just a, and a minus 1 gets replaced here. So that's for this sum. In this sum, I would reindex by replacing b with b minus 1, and this sum I would reindex by replacing c with c minus 1 everywhere. Okay. Shifting the minus 1 to the other side underneath the sum, that's where I get the a plus b plus c is equal to n plus 1. And then what I'm left with in each of these trinomial coefficients is a minus 1 from this sum, b minus 1 in this slot from this sum, and c minus 1 in this slot from this sum. Now, of course, you notice what it is going on here, right? And in fact, you could say, well, you didn't do this for no reason, and that's right. Like, the reason we were drawn to reindexing in this way was specifically so that this algebra would work out, spurred on by the fact that we know this formula. So we know when we have this on the right-hand side where we are adding a bunch of multinomial coefficients where we have minus 1s in all of the slots, like exhaustively, then this sums to the multinomial coefficient where there is no minus 1 here, and this has been incremented 1. So it was n minus 1 on the right-hand side. This is n on the left. So that is to say, these combine How do they combine? Just rewriting this. The sum is still over ABC such that A plus B plus C is equal to M plus 1. And this, by this addition fact that I've boxed here from yesterday, is N plus 1. Choose A, B, C times X to the A, Y to the B, C to the C. So that we have shown, in the case that there are three terms here, in the trinomial case, we have shown equality of these two things, which is exactly the statement of the multinomial theorem in this trinomial case for M plus 1. So that finishes the induction. If you are wondering how this works in the generic M case, now you know. I'm following the same process. I just have M terms, so it's just a little bit more unwieldy when I write it out. But I'm using the same addition property. And I have M terms, that's perfectly fine. The addition property is stated for a generic multinomial coefficient. So that is how it's done. So think about how you would just generalize this ever so slightly, right, to really nail this notation down. Okay. One more application of multinomial stuff. So, in fact, this application is maybe one that you would have, this is maybe one that you would have come across I know when I teach Stat 410. Oftentimes, this is the application of the multinomial theorem and multinomial coefficients that I use, because it is one of the more convenient applications of it. So what is the idea here if we talk about ordering a collection of n objects where the objects are not all distinct? So ordering a collection of n objects when there are duplicate objects. So the collection of objects might be like this. Let's say it's letters, right? So there's A, B, C, A, D, E, A, B. This is a set where I have multiple copies of the same element. Now, this is maybe distinct if you're using this notation to build your set, and you've previously, we've only used this when a set contains distinct elements. Having these repetitions technically makes our collection what is called a multiset. Of course, we talked about this previously in graph theory, right? So in graph theory, like on the first day of class, I mentioned what happens when your edge set is a multiset, right? So here, right? Here's 3 vertices. Oh, that's K3, but wait a minute. There. Right? So if we have vertices labeled ABC, the edge set of this, if this is a graph G, the edge set of G is, there's AB, there's AC, but then BC shows up 3 times. right? So this is an example of a multiset. So if you have a graph that allows multiple edges between two vertices, that's this was one of the cases that we didn't consider when we were talking about. Most of what we were talking about were finite simple graphs. So this was a type of graph that we didn't consider very much, but I did mention it as an option of something you could consider because there are applications for something like this. Okay, so how do we talk about ordering a collection of n objects when there are duplicate objects in this way, right? So, like for instance, how to order 4 poker chips, 2 of which are blue and 2 of which are red. So you have 2 colors here. There are 4 poker chips. 2 of them are blue, 2 are red. So how many orderings do I get? Well, there's red, red, blue, blue. Right? There's red, blue, red, blue. There's red, blue, blue, red. There's blue, red, red, blue. There's blue, red, blue, red. And there's blue, blue, red, red. And you can check with yourself real quick that these are all of them. So then what do you notice here? Well, you notice that, of course, there are less arrangements than if these were just 4 poker chips. So if these were 4 poker chips that were all distinct, say there's 4 of them, how many arrangements are there? Well, just 4 factorial, right? So 4 times 3 times 2 times 1, that's how many, right? So you get 24 total. Well, this is obviously a lot less than that. There are only 6 possible arrangements here. And you can think to yourself real quickly how you would compute the number of total arrangements here when you have some number of poker chips and there are one of 2 colors, right? So what about 10 poker chips and, say 6 of them are blue and 4 of them are red? How would you compute that? How would you count the number of ways to arrange those poker chips in this way? Well, it turns out that we can do this with multinomial coefficients. So I'm going to talk about how to do this. So we are going to reformulate our multinomial object. Okay, so suppose we have a multiset of size n that includes exactly k sub 1 instances of one object, k sub 2 instances of another object, and so on, ending with k sub m duplicates of the last object. Okay, so maybe you say there are m total objects, right? But we have a multiset of size n so that the number of each type of object, of which there are m types, is n. So the total number of objects is n, because that's what the size of our multiset is. There are m different types of objects, right? But each of these describes the number of each type of object, right? There's type 1, type 2, all the way to type m. Okay. So, note, the thing that is kind of driving the count here is the fact that among the duplicates, I can always rearrange how they fall without altering the actual overall ordering. What do I mean by that? Maybe it's a little harder to see here because there's not as many. So if I do an example here in a second about reusing letters, for instance, in a word, um, you'll be able to see it more clearly. But here, it means that I could swap this red with the first red, and it doesn't do anything. I could swap this blue with the first blue that shows up, and it doesn't do anything. Swapping these two blues does nothing. Swapping these two reds does nothing, right? In each of these examples. Okay, and that's why I'm undercounting what it is that's going on here. I can actually permute each of these amongst themselves, and I can't tell the difference because they are duplicate objects, right? I could label these. I could label this as the first red and this as the second red, and then when I swap them, there would be a difference, right? I would be tracking then each of the reds, but actually, right, that's not what the question is asking me. The question is just saying, how many ways can I make this arrangement? And I'm not actually tracking which red comes first. Okay. So, in this way, I can, when I do any of these ordering, I can rearrange the case of I copies of object I. So I can rearrange the case of I copies of object I in any way, and it doesn't disturb the arrangement. And it doesn't alter the arrangement. But I can do this for each of these things. I can do it for each of the case of I's independently, right? And none of them affect each other. So that's why this is an independent thing. So then how many times does each distinct ordering of the items occur? By the multiplication rule, so by product rule, the number of, or I should say, each distinct ordering of the items occurs. So distinct orderings of the items is, well, there's the permutations of the case of 1 objects, then the case of 2 objects, then the case of 3 objects, and so on, out to the case of m objects. Again, I can use the product rule because this is independent, right? At each step, this is independent. And so the number of distinct ordering of items is this, and this occurs among the n factorial total ways one could arrange the objects if they had been distinguishable, right? So number of arrangements of n objects if they are distinguishable. Distinguishable. Is n factorial. So if we go back here and we actually label This is the first red, this is the second red, this is the first blue, this is the second blue. And now I ask the question, overall, how many arrangements of these are there of these? The answer is 24, because there are 4 objects here that I'm tracking, R sub 1, R sub 2, B sub 1, and B sub 2. So now I'm distinguishing between each of the reds and each of the blues. So these are 4 distinct objects. So n factorial, 4 factorial, which is 24 in this case. So the number of arrangements of the n objects, if they are distinguishable, if we've put labels on them like that, is n factorial. So this number of distinct orderings of each of the items independently, this is taking place among the n factorial total number, and thus the number of distinct arrangements of our multiset is the following. What is this? What is this number? It is n factorial, the total number of ways, divided out by the number of reorderings you could do without being able to tell the difference. Oh, but we've seen that before. This is just our multinomial coefficient. So the multinomial coefficient is counting the number of arrangements of this multiset in this way. Okay. So let's go back to our example really quickly. Here, in our example, the total number should be 4 factorial over, there's 2 reds and 2 blues. So this should be 4 factorial over 2 factorial times 2 factorial, which is 4 factorial is 24. 2 factorial is 2, so this is 2 times 2, so this is 24 divided by 4. This is 6. And indeed, 1, 2, 3, 4, 5, 6. There are 6 ways of doing this. Okay. Of course, you can do this in, like, you could have developed the multinomial coefficient directly from this example if you wanted to do it that way. So another way of viewing this. Say that we have n ping pong balls. Okay, so we have n ping pong balls numbered 1 through n. So n ping pong balls numbered 1 through n. M boxes. Each is labeled with a different object from our multiset. So, for instance, if you thought of these n objects being colors, so there's red 1, red 2, red 3. Of course, all these reds are exactly the same shade of red. They're indistinguishable to us. We're just labeling them, right? So there's red 1, red 2, red 3, blue 1, blue 2, yellow 1, yellow 2, yellow 3, yellow 4, and so on. So the boxes would just be labeled with the color, right? So there would be the red box, which would contain, or you could think about putting all the reds in. There would be the blue box, where you're putting all the blues. Yellow box, where you're putting all the yellows, and so on. Okay, so that's how we have labeled our boxes. The number of ways to distribute the balls among the boxes, with case of 1 in box 1, case of 2 in box 2, and so on, is the multinomial coefficient, of course. So the number of ways to distribute balls into boxes with case of 1 in box 1, case of 2 in box 2, and so on is exactly our multinomial coefficient. This is how we defined our multinomial coefficient in this way. But of course, each arrangement corresponds to an ordering of the elements of the multiset. So the numbers in box I indicate the positions of object I in the listing, right? So, but each of these corresponds to an ordering of the elements in the multiset. Right? The numbers in the boxes, so the numbers in box I indicate the positions of object I in this list. Okay, and so we could have thought about this all along. We didn't need any kind of other additional reasoning, although this helps see exactly how this is being counted here. And so let's say we do an example. Say arrangements of words with repeating letters. So this is one of the best applications of using the multinomial coefficients to count something, because otherwise you would essentially have to derive them to do this count. So what is the idea here? Let's say we consider the town of Alma, Alabama, and we want to know how many ways can we rearrange the letters of this town and state, ignoring differences in case. So yes, we have capitalized these two A's, but we're not going to distinguish them from the non-capital A's, right? So question, how many ways to rearrange these letters? How many ways to rearrange these letters, ignoring differences in case? So for instance, there's the arrangement that they currently have. If I had swapped, say, these two A's, or this A and the first A, nothing would have changed here, right? So you think of, you look at this, I put the curtain up, I swap some stuff, I raise the curtain, and this is what you get. You can't tell what I did, right? Did I swap this A with this A, this A with this A? Did I swap any of the A's? Did I permute any of the A's amongst themselves? Did I permute the L's amongst themselves? What about the M's? I swapped this M with that M. You can't tell, right? So all of those get counted in the same instance. There's something that looks like Alma, Alabama, swapping any of the A's with any of the other A's here, swapping the two L's, swapping the M's. That's none of those would do anything. So I have to figure out, like, how many objects do I have here, right? So how many? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's an easy enough count. So 11 letters total. Now let's see how many I have in each category, right? So I have 6 A's. 1, 2, 3, 4, 5, 6. Yep. I have 1 B. I have 2 L's. I have 2 M's. And that is 11 total. 6 plus 1 plus 2 plus 2. Yep, that's 11. That's all my letters. Okay, and so the answer to this is the multinomial coefficient 11, choose 6, 1, 2, 2, which is 11 factorial over 6 factorial, 1 factorial, 2 factorial, 2 factorial, which is 13,860. Okay. Further question. Right. What is the number of four-letter sequences of letters So what's the number of four-letter sequences of letters that can be formed from the same string? The string in question is Alma, Alabama, so I'm just going to write it just letters, and I'm going to capitalize all of them so that there's no further confusion. Okay. Only they do not have to be English words. This is to distinguish it from a question that was asked earlier in this section. I didn't ask it, but there's a question asked earlier in this section in the textbook, except it restricts to the things having to actually be words. So do not have to be English words. This is four-letter sequences of letters that can be formed from the string here. And so what is it that's going on here? How do I count this? So the number of four-letter sequences of letters that can be formed from the same string. Okay, but I want you to read pages 148 and 149 to see how you would answer this by considering the process by which you would construct such sequences here, which is going to tell you how you should count this. Okay. So have a read here. It's not too long. It's like a paragraph and then a table. But this is good reading to see how exactly this works. Okay, so that's enough of multinomial coefficients for now. These are very useful. There are some problems that would be pretty intractable if you're not doing something that involves multinomial coefficients. So these sorts of problems involving rearrangements of letters where you have duplicate letters is one of them. This is one of the big uses of these things. Okay. Now, on to the pigeonhole principle, as I promised yesterday. The thing to know here is the pigeonhole principle is something that you have used before, whether you know it or not, and it might seem obvious. In a way, it is obvious. It's barely, the proof of it is barely a proof. It's almost true by definition, although there is a proof of it you can do, and I'll let you think about it because it's not long. It's like a one-line proof, essentially. And the pigeonhole principle itself might seem almost trivial, like almost something that shouldn't have a name, like, well, I mean, even like, the commutative property of addition has a name. It's just you're used to the addition of real numbers commuting, so you're not going to say, yeah, by the commutative property, it doesn't matter what order I add them in. But that's how you kind of might think of the pigeonhole principle, as being such a background thing. It's like so obvious that there's no need to even say it. But while it might seem like that on the surface, the pigeonhole principle is like kind of the main thing that allows you to assume that a certain structure exists when you're doing some of these counting problems. And so I'll do a few examples of this. We have already used this in a previous graph theory proof in Ramsey theory. We use this, but I'm going to state it as the following theorem, which is the pigeonhole principle. If you're wondering about the name, this is the name in English, and like every language, it's basically called something different. So I'll talk a little bit about the name after I state it. Let n be a positive integer. Okay, if more than n objects are distributed among n containers, then some container must contain more than one object. What's maybe the easiest way to see that this is the case, right? Well, you have n containers. Suppose that each container held at most one object, right? So suppose the max number of objects you could have in a container was 1. Well, then the max number of objects would be n, right? You would have one object at most in each container. There's n containers, so n would be the number of objects you had. But I was told that I have more than n objects being distributed. So that would not account for all of the objects. So yes, one of the containers has to have more than one object. Again, this seems very trivial. Where did we use this before in graph theory? Recall when we dealt with questions. Let me. Maybe I should say here. Recall our computation of R33, the Ramsey number. So what did we do? We first showed that it had to be bigger than or equal to 5. And we did that by considering k sub 5, right? Complete graph on 5 vertices. And then after that, we showed that we couldn't, we weren't guaranteed either red or blue k sub 3 in that case, so this had to be bigger than or equal to 5. Then to show that it was actually equal to 6, that in the case that we were dealing with k6, we had a blue k sub 3 or red k sub 3. To do that, we looked at k sub 6. Each vertex in k sub 6 had degree 5, and then we asked, well, how are the edges in a edge 2 coloring? How do the edges work? right? Well, I have two colors, red and blue. Each vertex has degree 5. So, like, the minimum number of either all red or all blue colored edges is 3. Like, what I mean by that is either, maybe, no, that's a bad way of phrasing it. I should say that the a vertex had um, either at least 3 red edges or at least 3 blue edges. One of those was true. It was impossible to have less than 3 red or blue edges because there would be an edge left out. And this is due to the pigeonhole principle. That's what we were doing there. Okay, so maybe that's a long-winded reminder of when we use the pigeonhole principle, but this is just one instance. So, um, the name, the pigeonholes refer to like the pigeonholes in an old type of wooden desk. It's the pigeonholes are these little holes, or even like the holes you use to pull out drawers in those desks. The pigeonholes themselves are little like compartments. So you're thinking of the in containers as in pigeonholes in a desk. Um, this is called the drawer principle in German. This is Dirichlet's naming. This is called the box principle in some other texts in like number theory and stuff. This is called the box principle. So, however you want to label this, this is what's going on. What are some examples of using this? Uh, well, there's say 400 freshmen enroll in some math course. Then 2 of them must have the same birthday. Why? You're distributing more than n objects amongst n slots. The n slots are the birthdays. How many possible birthdays are there? Well, 366, right? We're counting, you know, counting people born on leap year day, right? February 29th. Okay. Suppose n boxers schedule a round robin tournament. So each fighter fights each other fighter. Okay. And afterwards, no one is undefeated. So everyone has at least one loss. In this instance, then each boxer has between 1 and n minus 1 wins, so 2 boxers must have the same record. So each boxer has between 1 and n minus 1 wins. Thus, 2 boxers must have the same record. Think about how this changes if we allow someone to have been undefeated. Okay. All right. One more. It is estimated that the average full head of hair has 100,000 to 150,000 hairs. Okay. Assume, just to put an upper bound on this, assume that no head has more than 250,000 strands of hair. So we have some upper bound. So assume that the hairiest head is no more than 250,000 hairs. Okay. Well, city of Phoenix, and it's probably even larger now, but this was as of 20 years ago. City of Phoenix has over 1.5 million people. I'll write it on the next line. This means that at least 2 residents have exactly the same number of hairs on their head. The same number of hairs on their head. In fact, you know, this, this is something we could narrow down more if we toss out outliers, like people that are completely bald. We could toss out the outliers. We could still make this claim because there's not that many of them. So, right, you're not going to be throwing out everyone except 250,000 people. So, this is an example of just quick applications of the pigeonhole principle. In fact, in this last example, because of the disparity, we can actually say more, right? Like if the person with the most hairs on their head has 250,000 hairs, there's 1.5 million people. We have so many more people, since this is more than 6 times the maximum number of hairs per head. There have to be at least 6 people that have identical hair counts. So in fact, there are at least 6 such people. So think about this for a second, why this has to be. Because of how many more people there are than the boxes we are trying to fill. Okay? So this is giving us a hint of how we can actually say something a little bit more powerful than just the original pigeonhole principle. And that is going to be what we call the generalized pigeonhole principle. So what is the generalized pigeonhole principle? So let M and N be positive integers. If more than M times N objects are distributed among n containers, then at least one container must contain at least m+1 objects. Again, proof is basically the same as I gave for the pigeonhole principle. Imagine that each container contained at most m objects. If each container, there's n containers, contained at most m objects, then the maximum number of total objects would be m in each container, so m times n, total number of objects. But I just said that more than m times n objects are distributed amongst these containers. So if m times n is our maximum, I'm distributing more than that. This doesn't account for every object, so that would be a contradiction. This would be impossible. So yes, one of those boxes has to contain at least m+1 objects. Think about how this gets us exactly this fact that I said about Phoenix a couple minutes ago, right? Okay. So, one more theorem relating to these things. So suppose A1, A2, so on up to A sub n is a sequence of real numbers with mean or average mu. So, of course, this is just the sum of these things divided by n. Okay. Then there exist integers I and j with both of these being bigger than or equal to 1, less than or equal to n, such that a sub I is less than or equal to the average, and a sub j is greater than or equal to the average. Okay. The proof is actually the same. It's the same principle in effect. If there were no such i's and j's, then every element of the sequence would be either strictly less than or strictly greater than mu. But if that was the case, mu couldn't actually be the average. So you have to have at least one integer I such that a sub I is less than or equal to mu, and similarly you have to have at least one integer j such that a sub j is greater than or equal to mu. So that is the argumentation. This is essentially you are warping the words around and just applying the original argument that you used for the pigeonhole principle and the generalized pigeonhole principle of just supposing that you had like that the maximum you could put in a single container was m objects here. So here you're assuming that, yeah, you have an entire sequence where there's not one of these i's or j's, so that every single thing is either strictly less than mu or strictly greater than mu, both of which are not possible. Okay. So all of these facts that I've written down, pigeonhole principle, generalized pigeonhole principle, and this fact about sequences of real numbers, all of these seem very, as I said before, almost trivial in what you are concluding. So again, the confusion might be like why this is important enough to give a name to and talk about. But the reason for this is that you can make some extremely, extremely like powerful and otherwise maybe very non-trivial claims, essentially that entirely rely on the pigeonhole principle and almost nothing else. So I'm going to see a couple of examples of this so that you can maybe appreciate the power of these things. And so let's look at an example of using this. So first, let's apply this to monotonic subsequences of a sequence. So we say a sequence a sub 1, a sub 2, and so on out to a sub n is increasing if a sub 1 is less than or equal to a sub 2 is less than or equal to a sub 3, and so on. And strictly increasing of course, implies that these inequalities are strict. Okay, obviously you see the difference between these things, right? So, for instance, an increasing sequence, a constant sequence is an example of an increasing sequence in that case, but it is not an example of a strictly increasing sequence. So you likely have experience with these sorts of things. So decreasing, strictly decreasing, defined similarly. Okay. All right. So now consider an arrangement of the integers between 1 and 10. So for example, let's consider the following arrangement. So 3, 5, 8, 10, 6, 1, 9, 2, 7, 4. That's all of them. Okay, so here is an arrangement of integers between 1 and 10. Okay, so look for an increasing subsequence of maximal length. So let's see here. What sequences am I going to, let's see. So there's 3, 5, 8, 10. That's an increasing subsequence. It's even a strictly increasing subsequence here of maximal length. Well, I don't know if it's maximal yet, but it's of length 4, right? So 3, 5, 8, 10 is 1, having length 4. Let's see if we can find one that is longer. There's 3, 5, 8, 9. Okay, can we do anything longer here? The fact that this 10 is here, of course, matters, right? So as far as including that 10 in your sequence or in your subsequence. What else? What about 3, 5, 6, 7? But when I picked 7 here, I could have actually stopped at 9. So 3, 5, 6, 9 also works. And checking these, this is pretty much it, right? This is pretty much all, and all of these have length 4. Okay, so all of these have length 4. I wasn't able to find one longer. Okay. So what about a decreasing subsequence of maximal length? So now let's try to find some. So there's like 861 works. That only has length 3. Can we do better than that? Well, I could have done 862, but I can't go further than that, so that's also length 3. There's 864, but again, nowhere to go from there. Okay, what about 10? 10, 6, 1 will work. Also 10, 6, 2 will work. Let's see here. What about 10, 6, 4? There's 10, 7, 4. 9, 7, 4. But it seems like I can't get more than 3 here. So all these are length 3. Here's the question. Is it possible to find an arrangement of the integers from 1 to 10 Is it possible to find an arrangement of the numbers from 1 to 10, and by numbers here I mean integers, is it possible to find an arrangement of the integers from 1 to 10 that simultaneously avoids both an increasing subsequence of length 4 and a decreasing subsequence of length 4? Simultaneously it avoids both an increasing subsequence of length 4 and a decreasing subsequence of length 4. So, for instance, this arrangement clearly doesn't, since it has multiple length 4 increasing subsequences. It doesn't have any length 4 decreasing subsequences, though. So that's what lets us ask this question. Is a decreasing subsequence, this looks like the biggest it could be is length 3. Is there a way to arrange these that both of these, for instance, would have maximal length 3? Is what is being asked here in another way. And this is kind of like a hard question thought of from this angle. The answer actually is no. No, it is not possible. So, to see why this is, we have the following theorem. Suppose M and N let me use lowercase here. Suppose m and n are positive integers. A sequence of more than mn real numbers must contain either an increasing subsequence of length at least m plus 1 or a strictly decreasing subsequence of length at least n plus 1. So look at how this theorem applies to our previous example. We're arranging 10 integers. M is 3, n is 3, 10 is more than m times n, which is 9. So by the theorem, this must contain either an increasing subsequence of length at most, or at length at least m plus 1, which would be 3 plus 1 or 4, or a strictly decreasing subsequence of length at least n plus 1, which would be 4. It doesn't have that, but it does have the first. So the theorem guarantees one of those. And so in either case, we have one of length 4. So I cannot avoid length 4 there, answering my previous question in the negative here. Of course, the way that this is phrased, you notice, let me bring it back on screen, of course, the generalized pigeonhole principle. Very suspicious, very suspiciously phrased to match up with this, right? So I'm going to do this proof. The next thing I'm going to do is I'm going to mention an application after I do this proof. I'm basically that'll be enough for today's lecture. That I'm in the next lecture, I'm going to mention one more application of this stuff to approximating irrationals by rationals, and mention where you can find that. Then we're going to talk about inclusion, exclusion. So anyway, let's finish this. So suppose R1, R2, so on up to R sub mn plus 1 is a sequence of real numbers which contains neither an increasing subsequence of length n plus 1 nor a strictly decreasing subsequence of length n plus 1. So I'm supposing not. I'm doing this by contradiction. So this is a sequence of real numbers, and it's more than mn real numbers. So it's a sequence of more than mn real numbers. I have one more term here, extra. It's a sequence of real numbers that contains neither an increasing subsequence of length m plus 1 nor a strictly decreasing subsequence of length n plus 1. Okay. Okay. So for each I between 1 and mn plus 1, so for each index I, let a sub I be equal to the length of the longest increasing subsequence in this sequence of numbers whose first term is r sub I. So this is the length of the longest increasing subsequence in this sequence of numbers when I say this sequence, I'm referring to the one we started out with here. In this sequence, whose first term is r sub I, and d sub I is defined to be the length of the longest strictly decreasing subsequence So this is the length of the longest strictly decreasing subsequence, also beginning with this term. So r sub I here. Okay. So, for example, let's go back here to our example. So in our example here, okay, what is a sub 2? A sub 2 would be the length of the longest increasing subsequence that begins with the second term in this sequence, which is 5 here. So we could have 5, 8, 10, or 5, 8, 9 will work. Right? Both of those have length 3. Can I do better than that starting at 5? No, all of the length 4 ones started with 3. So no, starting with 5, the max I can get is 3. Okay. What about d sub 2 here in this example? So again, I'm starting here, and now I'm looking at the length of the longest strictly decreasing. It's going to be strictly decreasing anyway because these are just integers, or positive integers here. So 5 and then 1 works. 5 and 2, 5 and 4. That's it, though. It doesn't look like I can do longer than 2, right? So 5, 1, 5, 2, 5, 4 all work, but I can't get more than 2. So in this example, a sub 2 would be 3, and d sub 2 would be 2. Okay. Now, just because of these two numbers here, m and n are positive, I have more than m in real numbers. How is this arranged here? So first of all, I know that a sub I is between 1 and m, and d sub I is between 1 and n. Okay, and this is true for each I. Okay. And there are how many possible values for the ordered pair containing AI, DI? There are MN. This is just the product rule. Possible values for the ordered pair AI, DI. Okay. But there are how many such ordered pairs? I could start with any of these terms in the sequence, and I have labeled this sequence specifically to have more than m times n real numbers in it. There are mn plus 1 such ordered pairs. i.e. greater than mn is what matters here. Thus, we can use the pigeonhole principle. So finally, we've been waiting to see how we're going to be able to use the pigeonhole principle. This is how. So by pigeonhole principle, or generalized pigeonhole principle, if we're being a little bit more precise, what does this mean? There exist two integers, j and k, with j, say, less than k, we've labeled them like this, such that a sub j is equal to a sub k, and d sub j is equal to d sub k. Some of these have to be equal. Why? Well, this is us saying that now we are talking about the pigeonholes in question, or the boxes or drawers in question, right? Saying that two of these ordered pairs are in the same box or same pigeonhole or same drawer, saying that they have to be equal because these are the possible values of them. So we would put equal ordered pairs in the same box. Okay, this is just saying that there has to be at least one box that contains multiple ordered pairs, and whatever that is, we've labeled it with the indices j and k here for when they actually are equal. Okay, so we're guaranteed at least one such pair. So call this pair alpha and delta. So call this pair alpha delta. Okay, so alpha is a sub j, which is the same as a sub k, and delta is d sub j, which is the same as d sub k. Okay. Now, let's use this. So we're continuing the proof here. Let r sub k, r sub I sub 1, well, if we're calling this maybe the first index, we'll call this I sub 2 here. R sub I sub 3, and so on up to R sub I sub alpha. Let this denote a maximal increasing subsequence beginning with R sub k. And let R sub k, and we'll say R sub I sub 2 prime, R sub I sub 3 prime, and so on out to R sub I sub delta prime, denote a maximal strictly decreasing subsequence. beginning with r sub k. Okay. Now, if r sub j is less than or equal to r sub k, then if we started, remember we have picked j and k such that j is the one we've labeled that is smaller. So we get two indices from the pigeonhole principle. Call the smaller one j and the larger one k. Okay. So this comes before. So if r sub j is less than or equal to r sub k, then tacking that on the beginning here, r sub j, r sub k, r sub I sub 2, and so on out to r sub I sub alpha is an increasing subsequence of length alpha plus 1. Beginning with r sub j. But a sub j is equal to, well, the length of the longest increasing subsequence in this sequence whose first term is r sub I, or r sub j in this case. I just found an increasing subsequence of length alpha plus 1, but I said that alpha is a sub j. But that can't be, because I just found an increasing subsequence of length alpha plus 1. So, that's not possible. So then the only other possibility is if r sub j is greater than r sub k, then r sub j, r sub I sub 2 prime, and so on out to r sub I sub delta prime is a strictly decreasing subsequence of length delta plus 1, beginning with r sub j, but d sub j is equal to delta, sorry. And d sub j is supposed to be the length of the longest strictly decreasing subsequence beginning with r sub j. But delta is d sub j. But then I constructed a strictly decreasing subsequence of length delta plus 1. So again, contradiction. So what is the only thing that could have gone wrong here? It was supposing that we had a sequence of real numbers that contained at least mn plus 1 elements that contains neither an increasing subsequence of length m plus 1 nor a strictly decreasing subsequence of length n plus 1. That assumption is wrong. If that assumption is wrong, that's the statement of the theorem. So that's it. We're done. By contradiction. Okay. And that is that. So I think ending with that good application of the pigeonhole principle is a nice stopping point. I'm going to give you one more example of the pigeonhole principle in use. One more application at the beginning of the next lecture, and then we'll move on to inclusion-exclusion. So anyway, that's all for today's lecture. So I am going to stop here, and I will see you all next time.